Hello, welcome to a video about generators and transformers. We'll start with generators. Some generators use a fixed magnet to generate EMFs in rotating conducting loops for electricity production. EMFs are electromotive forces or voltage. In Stage 2 physics, you'll need to be able to explain how generators can be used to produce an electric current. So generators convert mechanical energy to electrical energy. An example of this is wind catching on turbines and rotating their blades. So that rotation is mechanical energy, and the turbine will then convert that energy to electrical energy. So for generators, a conducting loop rotates between the poles of a magnet. We've got a schematic here of that happening, and it is really important to remember that the loop rotates as a result of some external motion. So for example, the rotating turbines of a wind turbine. There's a battery here. That battery is where the electrical energy is stored after it's been generated. It's not powering the circuit, it's not providing the energy for the coil to rotate, because this is a generator, so it's generating power. So how this works, the conducting loop, which is the rectangle between the poles of the magnet, will rotate, and as a result, the flux, which is equal to the magnetic field strength multiplied by the area which the magnetic field strength is passing through, so in this case the area of the conductor. This continually changes as the loop rotates because of the changing angle of the loop relative to the magnetic field. So for example, if we look over here, we've got a loop that's perpendicular to a vertical magnetic field. So the magnetic field will be passing through the maximum possible area for that loop. As that loop rotates, eventually it will become vertical or parallel with the magnetic field, and so there'll be no magnetic field passing through the loop because the loop is perfectly parallel with the magnetic field, so there's no area perpendicular to that field. In between this point and this point, the area that is exposed to that magnetic field will be gradually becoming smaller and smaller until it goes all the way to zero. So if you think about it rotating, but then try and imagine, this is how I think about it, so if it's rotating, if you imagine yourself looking down on top of it, the area of that loop will become narrower and narrower if you're just looking at it from a horizontal plane, and then eventually it'll just be a straight line when it's vertical if you're looking down from above onto it. From this point here, then it will continue rotating around in this direction. Eventually it will become perpendicular again, and then the maximum amount of area will be perpendicular to that magnetic field, so the flux will be at a maximum again. Some more revision from previous learning. Change in flux induces an EMF, which is a voltage, in a coil. So given that, because the loop is rotating, then the area exposed perpendicularly to the magnetic field will also be constantly changing as it rotates. Therefore, the magnetic flux will constantly be changing, so there'll be that constant change in flux, which is inducing a voltage in the coil. So ultimately, the current flows from the coil where it's been induced to an external circuit, and that's where this battery is connected to, so this external circuit here, and it flows to that circuit via metal brushes, which are these little, I'm going to get a different colour, these little black rectangles here. So they're pressed up against some rotating slip rings, and those rotating slip rings are directly attached to the rotating coil, so that's how the current is transferred to that external circuit, and then that electrical energy will just be stored in a battery, or it might be directly connected to something in place of the battery, and the generator will be powering that. So moving on to transformers. Transformers allow generated voltage to be either increased or decreased before it is used. A transformer consists of a primary coil with NP turns, so the number of turns in the primary coil, and it has a potential difference of V and then a little p to indicate that it's the primary coil's potential difference. Secondary coil similarly has NS turns, so number of turns in the secondary coil, and the potential difference is represented with V and a subscript S. The relationship between the potential differences is given by this formula here. So it's just a ratio, the ratio of the primary voltage to the secondary coil's voltage is the same as the ratio of the number of turns in the primary coil to the number of turns in the secondary coil. So if you're looking for any one of those four values, you'll just need to rearrange the equation and sub in your known values in order to find that unknown value. In stage 2 physics, you'll need to be able to describe the purpose of transformers in electrical circuits. You'll need to be able to compare step up and step down transformers. You'll also need to be able to solve problems involving this equation. So transformers increase or decrease alternating voltage. They consist of primary and secondary coils, as we've already discussed, and these coils are interwoven with insulating wire or a laminated iron core. And the reason the wire or the iron core is insulated or laminated is to reduce eddy current losses, and we'll touch on that in a moment. So what happens is there's an alternating current that flows through the primary coil, and because this current is constantly changing direction, the magnetic field, so if you've got your right hand rule where you've put your thumb in the direction of the current and the way that your fingers are wrapping around that wire, if you imagine that you're holding it, that's the magnetic field. So that magnetic field is constantly changing because the direction of the current is constantly changing. Because there's a constantly changing magnetic field, that means that there's a changing magnetic flux as well. So that's what this is saying here. The changing magnetic field passes through this iron core. The secondary coil is located within the range of this magnetic field because it's wrapped around this iron core, and because this magnetic field is constantly changing, that means that an EMF, an electromotive force, a voltage, will be induced in the secondary coil. So electricity and magnetism are related. So if you've got an electric current, there'll be a magnetic field that surrounds that current, that electric current. If you've got a conductor that doesn't have any current flowing in it, but you bring a changing magnetic field along and expose that wire to the changing magnetic field, then that changing magnetic field will induce an EMF, a voltage, and it therefore will induce a current in that conductor. So they can induce each other. An EMF will be induced in the secondary coil, and that EMF is dependent on the number of turns in that coil as well as the number of turns in the primary coil. So just touch on energy losses within transformers. So there's electrical resistance within the coil, so as a result energy will be lost as heat, but there's also energy lost via eddy currents which are produced within the iron core. So because the iron core is a conductor, eddy currents will be produced by the change in magnetic flux within that conductor. As a result, eddy currents circulate within the iron core, and therefore unwanted or opposing, like magnetic fields that are in the opposite direction, are produced by those eddy currents, and energy is wasted as heat due to resistance within the core, so resistance that those currents face. So the eddy current energy loss can be reduced by laminating the iron core. So rather than having this big chunk of iron in the core, you divide it up into segments, and each segment is laminated. This laminating increases the electrical resistance between each section, so the eddy currents, rather than being able to circulate around the big block of iron, are confined to smaller areas. Because they're confined to smaller areas, their voltage, their EMF, will be smaller, and resistance, if you remember your V equals IR equation, resistance will be equal to voltage divided by current. So if you're decreasing voltage, which is EMF, then you'll be decreasing resistance if the current is the same. So because you can't really prevent eddy currents from occurring because they're just a natural phenomenon, you have to try and minimise their impact. And you can do this by decreasing the space that they're able to run in. So the EMF induced in the secondary coil depends on the number of turns in the primary and the secondary coils, and we'll use these rules here to get this rule here. So it's just derived from Faraday's law. If we were to make a ratio of these sums, we'd end up with V primary, so voltage in the primary coil, over voltage in the secondary coil, and that would be equal to number of turns in the primary coil multiplied by the rate of change in flux, and then divide that by the number of turns in the secondary coil, also multiplied by the rate of change in flux. These values here are equal to each other, so they will just cancel out, and you'll be left with this equation or this ratio here. So the voltage in the primary coil, or the ratio of the voltage in the primary coil to the voltage in the secondary coil, is equal to the ratio of the number of turns in the primary coil to the number of turns in the secondary coil. So as a worked example, you've got a transformer that's built into a portable radio to reduce a 240 volt supply to 12 volts. If the number of turns in the secondary coil is 100, how many, that should say turns, are in the primary coil? So we'll just use our ratio, so we'll write that Vp on Vs is going to be equal to Np on Ns. Our Vp is equal to 240 volts. Our Vs is equal to 12 volts, and we know that the number of turns in the secondary coil, Ns, is equal to 100. So we are looking for the number of turns in the primary coil. To find this, we'll just rearrange the ratio, so we'll end up with Np is equal to Ns multiplied by Vp over Vs. That will be equal to 100 multiplied by 240 divided by 12, and we'll end up with 2,000. So there's 2,000 turns in the primary coil. Next question, a transformer, that should say has a primary coil. A few typos here today, sorry. And the primary coil has 2,400 terms, so primary coil has 2,400 turns, and secondary coil has 120 turns. What is the voltage in the secondary coil if the voltage in the primary coil is 240 volts? So voltage in the primary coil is 240 volts. We've got our Vp on Vs equals Np on Ns ratio. This time round we're looking for the secondary voltage. So if we rearrange this equation, we'd get, you can do it how you want. You can just flip the numbers if you want, or flip the fractions, but the long way of doing it would be Vp equals Vs Np Ns, and then you'd move to multiply both sides by Ns, so you'd end up with NSVP, and then you divide both sides by Np. So hopefully you can see you'd end up with Vs equals NSVP over Np. This would be 120 multiplied by Bp, which is 240, divided by Np, which is 2,400. And that will, if you pop it all in your calculator, bring you to 12 volts. So the voltage in the secondary coil must be 12 volts. So finally we'll have a look at step-up and step-down transformers. This is pretty intuitive. A step-up transformer means that the voltage in a secondary coil is getting stepped up from whatever the voltage was in the primary coil, so the voltage is increasing. Therefore, the number of, turns. Number of turns in the secondary coil is going to be greater than the number of turns in the primary coil. Conversely, in a step-down coil, the voltage is decreasing, so the voltage in the secondary coil is going to be less than the voltage in the primary coil. Therefore, the number of turns in the secondary coil is going to be less than the number of turns in the primary coil. Now, the power in both primary and secondary coils must be equal if energy is conserved. Power, the rule for that is P equals VI, so P equals voltage multiplied by current. I've just got the reverse here. So whatever the current is multiplied by whatever the voltage is in the first coil, or the primary coil, that value has to be equal to whatever the current is in the secondary coil multiplied by whatever the voltage is, or the voltage that's induced in the secondary coil. So those two values have to be the same. So if you've got a situation where the voltage in the secondary coil is increasing, but voltage multiplied by the current has to be equal to this value here, then your current must be decreasing. So in the step-up transformer, your voltage is increasing in the secondary coil, you've got more turns in your secondary coil, but to compensate and to make sure that the power is equal in both the primary and the secondary coils, the current of the secondary coil must be less than the current in the primary coil. Conversely, in the step-down transformer, if your voltage in the secondary coil is less than the voltage in the primary coil, and therefore your number of turns in the secondary coil is less than the number of turns in the primary coil, to compensate for the fact that the voltage is less but the power needs to be the same, the current in the secondary coil is greater than the current in the primary coil. So if we write that out, that would be IP Vp equals IS Vs. I'll get this guy here. So if the voltage is decreasing in the primary coil, but the overall power needs to be equal, voltage is decreasing in the secondary coil, the overall power still needs to be equal to the primary current multiplied by the primary voltage, then the secondary current will need to be increasing in order to compensate for that decrease in voltage if the power is the same. Step up and step down transformers are used in electricity transmission. So when electricity is being transmitted, it is transmitted at a really high voltage, and this is to reduce power loss. So power loss is equal to current squared multiplied by resistance. So you want to try and reduce the current as much as possible. So to do that, reducing the current as much as possible, you want to increase the voltage. So the power that is transmitted is still the same, and the power loss, so this is a rule for power loss, the power loss is reduced. So that's why electricity is transmitted at such high voltages. Eventually the electricity will get to a substation and there'll be a step down transformer here. So this might reduce the voltage to a lesser amount as it's getting closer to wherever it needs to be used. And then eventually there'll be a step down transformer located at the home, and this will step the voltage down to 240 volts, and 240 volts is the standard voltage in this country. I think voltages tend to vary around 220 to 240 around the world, but there are some countries that use 110. I think Mexico uses 127, so it does vary depending on the country that you go to.